Okay, thank you very much. Good evening, all. So I'm Ioannis Papdatos, Geotechnical Manager in Balfour Beatty MSc. So this presentation will include an HS2 project overview, and we're going to speak about the two tunnels that one has been completed, one is ongoing. Is the two tunnels on the north part of HS2. The one is Long Easington Wood Tunnel, and the other is the Bromford. We're gonna speak about the tunnel overview, the characteristics. Then we have to have the geological setup. We're going to talk about instrumentation and monitoring, what has been installed, and how we are doing ground inspections during tunneling, either through the TBM or on the cross passage traditional tunneling method. And then we'll see some monitoring summary in terms of volume loss and how the performance and what that we have achieved so far. The Bromford tunnel, basically we're going to speak about the same subject, and what was that we follow the same design approach as Long Easington, but in this case, this tunnel, which is ongoing, is much more critical because it's longer, and it crosses an urban area, and that's why the instrumentation monitoring system has been applied. It's much more comprehensive, and we will discuss about that, and then we will see some readings we have so far, and then we have the conclusions. So, as an HS2 overview, maybe more all of you know. So it's a new high-speed railway which is built from London to Midlands, and the length is 140 miles. There are 4 new stations in this alignment, 2 major depots, 32 miles of tunnels, and over 500 bridging structures. So Balfour Beatty Vinci JV, we call BBV, has been awarded the contract to construct the northernmost 90 kilometers of the HS2 route, which start from Long Easington, the tunnel, which is the first part of our project, is the one of the tunnels, which is in Warwickshire, and then this goes to the start from the south and it goes to the north, and enter one branch, go west and inside the Birmingham city, where we have the second tunnel, and one branch goes northern, where it will eventually join and connect to the west coast main line. So this contract is 90 kilometers, we said. It has, among other things, viaducts, 11 kilometers of viaducts, 62 overbridges, underbridges, embankments, cuttings, underpasses, and there's a lot of works, of structures. And then we have the 2 tunnels, which we are going to further analyze in this presentation. So the Long Easington, this is a tunnel has been built. This is the photo that you can see here is from December 2021, where we had the launching of the first TBM on from the north portal. This is the north portal, and this tunnel has been constructed with 1 TBM, which has been complete the 1 drive, and then dismantle all the pieces came back, and then again put it together and start the second TBM. So we have 2 single bores of 1.6 kilometer. This has also 3 cross passages, which are connecting the one bore, the up line with the down line. As we said, we use one TBM called Dorothy. Excavation diameter of the cutter head was around 10 meters, and the internal diameter of the tunnel was 8.8 meters. The segments, there was a segmental lining, which was like TBM as is constructed during the advancing. So we have 400 mm thick rings, with each ring had 2 meter length, and the full ring was comprised by seven segments plus one key, we call it, and was steel fiber reinforced. We had also reinforced rings on the portals and on the locations where we have the cross passage to mitigate the additional stresses. So this tunnel, including the cross passage, has been completed. Now it has been completed 100%. In terms of geology, this is the layout and one extra from the 1 to 50,000 scale geological map of the area. So we have on the, let's say, called the northern part, we have the, which is here. Sorry. Yes, sorry for that. So here we have the Mercia Mudstone Group, where we meet the Sidmouth formation, all the formations that we see on the next table. And then on the close to the exit along the drive, which is the south portal, we have encountered the Penrith group, which was overlying the Mercia group. So it will be it's better to see the section. So that's the section. This is the north portal, where you have seen the photo, and this is the hill that has been it was the reason of the tunneling. It was an ancient woodland that has been crossed, and both drives has been from north to the south, and the ground condition. We start with it was Mercia Mudstone, which we have the three formation, the Sidmouth formation, the brown scope, and the blue anchor. And then we have on the overline, we have the Penrith group, Westbury and Cotham for mudstones, which we encounter towards the end of the drive. The ground is a soft rock, actually. It's a mudstones, soft rock. It's a weak ground in terms of uniaxial compression strength. And there was a lot of discussion before the tunneling. Now we know, of course, but there was a lot of discussion regarding weathering zones, and basically what will be the water ingress in the tunnel. And we had the two different aquifers. We have the low aquifer, which was in the Mercia Mudstone, and the shallow aquifer, which is in the Penrith group. However, due to the low permeability of material, we encounter not major problems in terms of excavations when we have to stop with the TBM and when we open the cross passages. The design approach was traditional, usual. We had a GI investigation, and once we have the lab test parameters, and there was a lot of work has been done the past years to define the characteristic values. There was a big discussion, as I said, regarding permeabilities, because the test in the GI does give some very isolated area, and we're not very confident that there will not be higher ingress in the ground. that's why we had to introduce uncertainties in the design. However, as I said, in this particular tunnel, as we know now, the permeability was quite low, and we didn't have much of the ingress. Then we follow the ground movement assessment design has been adopted in order to define the settlement and the impact that the tunnel will produce to the ground. The typical use, the Gaussian curves has been used for this design, and the volume loss of 1% has been assumed for the TBM, and 1.5% for the traditional, let's say, excavation, the SCL sprayed concrete lining cross passages. This was given also from the HS2 and the trough parameter on the Gaussian curve analysis has been given. The trough parameter was taken as 0.4. So that was what it was assumed in the design, and how they were calculated the expected settlements during the tunnel. Then the second part was to define the operational parameters of the TBM. So the TBM is working in a way that has to balance the earth pressure and the water pressure. So based on the GI and the assumptions and the covers and the waterhead, there was an equilibrium of ground wedge and water pressure design along the tunnel to define the envelope, let's say, of the upper and lower bounds of the face pressure for the TBM. And so upper bound basically is defined as a vertical total stress above the tunnel. In some cases, we have some limitation from the design. I mean, pressure cannot be beyond a certain limit because the designer of the segmental lining do not allow that. But in general approach, we didn't want to have any to go beyond this, of course, vertical total stress. And the lower bound is to support the wedge, support the face pressure and the water pressure. So to be always a bit above that. And grouting is a second part that has to be above the confinement pressure. So this design has been done, and for the tunnel, and has been applied, and we're going to see later what was the performance. Now, instead of instrumentation monitoring in this tunnel, there was not so critical. Let's say, assets. It was a countryside, more or less. There were a few houses. So mostly the monitoring, it was done in order to be able to understand the behavior of this TBN in the Mercia Mudstone. As we see, there was no much tunneling experience in Midlands. So we haven't got a lot of reference for that. So the monitoring that we have used, it was the usual the leveling stats to get leveling records. And we had let's say on areas where we have a hard ground, we were using some pins, some studs. Where we had soft ground, we have to use some concrete pads. And in other places where we have very soft ground, we have to use some longer nails, deep anchors, survey anchors, deep anchors we call it, in order to mitigate any surface and seasonal variations. And then we have manual leveling readings daily when we have the TBM crossing, and then weekly and monthly. This was defined on the design monitoring plan that we had. And then we additional on the surface monitoring, we have the deeper monitoring, the borehole instrumentation, which was again typically inclinometers, extensometers, piezometers, standpipe piezometers, open tubes, and fully grouted borehole piezometers for pore water pressure. We try to be able to automate it as much as possible of the instruments, and mainly that was what was only possible with the borehole instruments. So we had installed some gateways in order to be able to have directly all the data to our database, monitoring database. And the one house that we were crossing, actually, we also install all the possible monitoring in order also for us to test how it works, how it behaves, and what data we'll take, and to set up also our database. So we have installed leveling studs in the building on the lower parts, and prisms, crack meters wherever there was a crack, and also a triaxial automated till meters, so we can have also automated results directly sent to the database. So in order to follow up this and to understand, we set up 4 basically monitoring areas along the tunnel. The 3 of them were just in the position of the cross passages, and the third one we had a flat area, and there we said that we need to do some verification zone. So we install some automated system for only verification. It was just a green field. There was no other purpose rather than to get more detailed results and to understand the impact of the tunneling. The other 3 arrays was on the cross passages, which will be used also for the tunnel, but also in the second stage during the cross passages. So this is the first array, some results. So this is the arrangement. We had the extensometers above the tunnel. We have inclinometers for the lateral, and of course we have the leveling points, which we have. That was within the Hessian woodland, and here you will see the volume loss. The red is the 1%. I mean, what it would be expected if we were reaching 1%. 70% was the yellow, and 50% is the blue. So this was for us, it was working as a trigger values. And you see here that this is quite scattered. The readings that we had was quite scattered on this particular area. So it was the first area that we are, and the first monitoring area that we had, and it was a bit annoying for us seeing such results. However, because the first TBM from the second TBM, it was more than like a 1 year difference, passing from the same location, and we had a long monitoring result. We understand that the TBM impact was this minor thing. It was like 2 to 2.5 mm, and then during the summer, we have a long shrinkage of the ground, which was much more way beyond any impact of the tunneling, and then we have some swelling also. So that was this particular. It was happening on the NCA woodland, which was a very nature area that there's no activity, and there was developed a lot of soft ground. So for that reason, we think that we cannot, because it was also the first array. So we said that we have to mitigate this problem of the seasonal variations, and because we need to capture only the impact of the tunnel itself. So for some reason, we have added deep survey anchors. We install additional there, and then we change also our mind for the next tunnel with Bromford. Wherever we have a soft ground, in order to mitigate that, we were installing much deeper level anchors. Then the second array was on the crossing of the road, which was also close to the CP2. So on this one, the results was much more better. But at the end of the day, everything was less than 5 mm. Just they have a we have some better results. And this is the arrangement. We have also some inclinometers either side. And this is the position in terms of the cover on this position in the geology where the tunnel cross. And at the end, the CP3. Sorry. This is the verification zone. So the verification zone, you see, we have a better results that has been given from the instruments. So in the verification zone, we have a number of instruments, and in this particular area, we try to install an automated ATS, we call it, automated total station, and we had the prisms on the ground, and we try to see that what is the actual impact comparing to the TBM crossing because this is hourly taking readings and directly sending to the monitoring database. We're able to see to define the TBM position against any monitoring settlement on the ground. So in this way, we had the better results. This you can see, of course, the spikes that it's usually coming in when you have a very frequent readings, and this is due to the day. You have a cold, you have frozen, you have sun, and so we have some spikes. However, we were able to minimize the spikes less than 0.2 mm and have some results, better results of the order of 4 mm that we monitor in this area. And finally, we have the fourth area, which is on the CP3, and there we have leveling points, and we have a good results. We have a very minor settlement, and the volume loss was, of course, very small. Although this was an area that the cover was less. However, we were managing with the TBM operation to pass by with a very minor impact. Of course, there was no utility, or there was no any other asset above that it was for us a bit stressed. More or less for us it was to see and achieve the performance of the machine, how it works and how it can adjust the parameters in order to produce the lowest impact. So during the excavation, from the TBM excavation, we whenever we had the opportunity, and the opportunity it is when the TBM stops for maintenance, and the pressure, the confinement pressure is reduced to 0, and they empty the chamber. So we have a small opportunity to go and check. And on the very top, there's an opening that you can visit, the cutter head. And basically, for the miners, this is an opportunity to check the discs and to change the disc and the scrapers if required change. For us, it's there for taking some pictures and after some cleaning and see the geology. That was the first time that we were able to see the Mercia Mudstone from the underground through the cutter head. There was small openings. However, we were able to confirm the section. So here, that was this location here. So we see the seismic formation, and then on top, and then the top we see the Arden sandstone. So it was a small one here. So we managed to understand and to see the contacts. Another example was close to CP2, where we were able to see the branch conformation, okay, how it developed, and on top we're able to see a bit of blue anchor. So, and here is where we see basically the branch conformation on the bottom, and on the top we see clearly the blue anchor. Just want to say that if you see it's only a small window on the top of the TBM. We couldn't see. You cannot see below. First of all, the chamber is full with slurry above the middle, and you don't usually empty because you don't want you want to maintain a pressure on the system in order to not to allow the ground to relax, let's say. So it's always like that, and you only have some visual visibility only on the top of the cutter head. And yes, one more. It's where we see the blue anchor, and then we see on the top we see the contact with the with the blue anchor, and we top the mass. No, the top is the blue anchor. Sorry, and sorry, in the Westbury formation. Yes, and here is with the contact. We see the blue anchor on board and the Westbury formation. So to be able to confirm this, and it was confirmed also this position of the section. And then after the completion of the two drives, we started the cross passages excavation. So in the cross passage excavation, we have 3 cross passages. We were able to actually see and be able to understand better the rock and how the Mercia Mudstone is behaving in the tunneling wear or in geology, and to see is there any water ingress, to understand the permeability, the structure, and we had its cross passage is around 10 meters. So we had let's say 10 to 12, 13 steps of excavation. So for each excavation, let's say an inspection log has been created, and we had a very good description of the rock and the geology and the hydrological conditions. So this was the way that we know that the water ingress was very narrow, very small, and it was good for our SCL excavation. Before we start any SCL excavation, we're doing 5 probes as an investigation at the 4A and 1 in the center. So to understand what is to see if we have any surprise. But however, the general excavation went good without much of surprises, and the rock behaved quite well in terms of stability. That is the CP2 area. We have an excavation CP2 where it's full of in Brascombe mudstone formation, and again we had the similar excavation logs for each excavation step. And in CP3, this is, you see the on top or most of the excavation phase is the blue anchor, and below we see the branch scope and the estimation by the geologist of the contact. So in conclusion, we can say that that was the first Long Kensington Wood. It was the first tunnel completed in HS2. That was happened in March 23, both tunnels, and we had quite good results in terms of impact, and very minor settlement recorded. And so it was a successful history for us, and it demonstrates that our approach, our strategy was suitable for controlling the ground. So that gave confidence to BBV and gave significant experience for the second tunnel, which is the Bromford tunnel, which it would be much more critical, because apart from the geology and the length, it also has to cross a lot of critical assets that we'll see in the next slides, and that was the main concern for us. So I'm going now to the Bromford tunnel. This is the east portal. So in the east portal, we have this has been is constructed with 2 DBMs. This is the down line and then the up line. And this has been, it's 5.8 kilometers length. Currently, the downline is around, maybe it's not 78, maybe 79%. And the upline is around 51% completed. And we have, as I said, 2 TBM, and there will be 13 cross-passers. The cross-passer has not been started yet. They will start it after the completion of the 2 drives. And this excavation diameter is a bit smaller than the other. It's where the train is decreasing speed, so you need a smaller diameter of the tunnel. And there is a intermediate shaft at the middle of the drive, which is 20 meters diameter. So in a geology setup, this is full in Mercia Mudstone in one formation, Sidmouth formation. That's why it has been separated in weathering grades. So we have the grade 1, 2, which is let's say the most competent. Still, it's a weak rock, but it's the most competent part of the weak rock, which we see fully the bedding and the structure of the formation. And then we have grade 3, which is where the formation and start getting more gravelly, and then it's loose. You cannot even see the formation sometimes, and it's gain more sandy and gravelly. And then and the behavior is start to become soil behavior. And then we have the grade 4, which is it's like a clay material, totally weathered material, which is behavior like a soil. In terms of groundwater condition, all the tunnel is the water is considering to be on the ground level almost, or 2 meters below ground level, and so it's fully submersible. And the material permeability is considered low, as we had the experience from Long-Keystone. However, in this case, we have some experience with more ingress of water in some of our cutter head intervention. So that's the criticality of this is that we have a lot of asset owners, which is basically the major, which is Netco Rail, National Grid, and National Highways. There are a lot of utilities, critical utilities like ESO, pipeline, and Cadent Gas. And we also cross 4 times, the alignment goes parallel to the Tame River, and we are crossing 4 times the Tame River, so we have to deal also with environmental agency. So there were a lot of third-party asset owners, and we had to go to each of them and get the necessary permits before even start the tunnel. So the same approach, design approach, has been used. The GI, the characteristic parameters, the ground movement assessment, and the confinement pressure design, which defines the envelope for upper and lower confinement pressure for us. Okay, it was similar. We followed a similar thing that was successful in the previous project. And we try to be a bit more innovative in a way of an INM system, because we have to deal with particular asset owners. So, and we have to go to them and discuss the monitoring arrangement for their assets, the structural monitoring, let's say, apart from the ground monitoring for the greenfield. And we have to discuss with them to agree to serve the needs of the specification of each owner, to be able to safeguard the structures, to maintain serviceability during the tunneling, and to be able to alert them in case that we had some breaching. So for that reason, we always install automated systems, and for time alerting, and also manual system, in order to be able to confirm and to validate the results of the automated system. That was a long time job and a lot of discussions and meetings with all the asset owners. And then all the monitoring data are directly going either automated, or the automated system they feed the database automated, and every day we upload also the manual leveling, let's say, monitoring to our database. It's called Mission OS. which you can also track the TBM live. And in case we have a breaching of any trigger value, we are sending directly emails. And further to that, as per the HS2 process, we have a shift review groups meetings daily, discuss the monitoring. And every week, we have 1 week where we are also discuss with designers. It's a more broad technical committee. And we also invite the asset owners. And in case we have any breach, like we have a management action team that in case that we have some red or black or amber or red, anyway, we have a particular action plan which we are taking place within depending on the breaching, within 6 hours, 12 hours, we have to respond. So yes, that is the three major asset owners. It was the one is the NetCorel, which is a 19th century embankment and the underbridge. The B is the B is actually the M6 viaduct, which is the longest viaduct in UK, operational viaduct, which is built in 70s. And also we have 10 lattice girder towers with high voltage cables also built in 70s that we have to deal with because influence zone is crossing this as well. So in NetCorel, we have to follow NetCorel requirements. We have to install automated total station. We installed 11 ATS total stations, more than 3,000 prisoners and instruments and till meters on the tracks. And on the underbridge, we have a particular agree with the NetCorel assessment with SAAs and till meters also. And everything had to go automatic. And we had every hour readings and sent every 6 hours to our server and have the readings online for available to everybody, including the asset owners. And both tunnels has been crossed this area. We are happy for that. And it shows actually negligible effect. So after that, also NetCorel allow us to remove all the instruments which we have, and we are doing the decommissioning this time. The second was the M6 viaduct. That was even the most critical, let's say, which there was a lot of designs support this structural instrumentation. We had a lot of instruments on the structure further to the ground instruments. And we were having hourly readings, and we have several we have several meetings with daily meetings and weekly meetings with National Highways. 1 TBM has already crossed. It was very good results. We have very even no significant not at all movement. We managed to measure on the structure itself, only on the ground, but the structure was intact. So also we give us more confidence. And in April, the second TBM also will cross by. So it will be a big milestone for us if we cross the second TBM under this structure. This is the results that we have. You see the usual automated spikes, but we kept everything within the acceptable limits, which was very, very, very tight. It was like 4 mm. We should not exceed 4 mm. That was very tight for us. We were afraid of having some spikes and having some unnecessary breaches and unnecessary, which it happened one time with the National Highways, but in generally we managed to maintain within this level. And finally, it was the National Grid. This was more simple. We have on the legs, we are putting leveling points and reflecting targets. And we had also automated till meters on each leg in order to be able to have automated results as well, not only manual. And here again, we had very good results with no very minor impact during TBM. Finally, I will just want to give you some indication about how this behave on this the greenfield. So we have the greenfield area. This is the area of the launch, which is a low cover. We have quite this is more strict. It's the trigger values that we have, but however we managed to have a quite low volume loss. The red is 0.5%. We managed to have much less in all these crossings. Then we have also here, we have another verification zone, which we install a lot of instruments in order to be able to understand the behavior before it goes into the urbanized zone. So this is the area of the site. So we had our land, so we were taking advantage of this, and we install a large number of instruments. Also here, the behavior was quite good. And finally, this is on the urban area. Still, this is the TBM1 that is been ahead within the urbanized area of Birmingham. However, since we still have quite good results. This is quite interesting. This is the extensometer reading. The extensometer is a borehole instrument that extended to the below, just so up to the cover, up to the crown of the tunnel. And usually we have 4 or 5 sensors. So because these are automatic every hour taking readings, we are able to understand as the TBM is approaching the instrument, what is the behavior. So what we basically see is that only the sensor, which is just above the tunnel, up like say 3 meters above the tunnel, has been impacted. But this is only a couple of millimeters, not more. And the other sensors above didn't show any impact. And we analyze furthermore to understand when this impact happened, and this to see as the TBM is approaching, is there any influence ahead or behind? So we managed to understand that it's coming just directly at the end of when the TBM the cutter head reaches this area. So we have the first drop, and then when the TBM is there, with under the sealed is still continuing, and then when we are installing the ring and we grout back, then we have a straight line after that. So it needs around 12 meters, 6 rings to pass through, and from the previous stability to go to the stability after tunnel, post tunneling. And the good thing is that vertically, let's say the relaxation zone of the tunnel of the ground was not more than 4 or 5 meters. We didn't see more because this was 3 meters and it moved, but the above it was around 7 meters, didn't move. And similar, this is a more this is the same, but a more the displacement with ring by ring to see exactly. We can analyze exactly how it behaves with the pressure and with the confinement pressure, and then the cutter head, and then the sealed, and then the grout. And we had this same picture we had in other areas. Again, only the bottom sensor has been moved, and not the other ones. So we are achieving, and we are more confident that we maintain the movement and the relaxation zone with the TBM in the Mercia Mudstone in this geology in an area of like 3-4 meters around the tunnel only, and then we are able to kill any further settlement. And then that is the inclinometer, which shows the lateral movement on the TBM. So we have some we see that the lateral movement, we have several positions, and we see the tunnel. On the tunnel level, we have a lateral relaxation, which is not expanded above. So it stays there, and then after the TBM cross, it stops increasing. So as a conclusions, we have the case history along Kensington Tunnel, which was not critical, but it was first tunnel in Mercia Mudstone and using this particular TBM and this method. So we demonstrate, and after this completion of the approach of the design, it was successful in order to control the ground movements. Then we share this with the tunnel teams and to perform in the Brofond tunnel. We increase the monitoring, instrumentation, all the arrangement because the Brofond tunnel was much more demanding. And so far, we are quite happy. We have no structural impact and volume loss below the expected by the design. So the TBM has crossed already the main assets. Okay, at least the TBM1 has crossed the Netco, the M6 viaduct, and the Netco rail, and some of the river crossing. So we get also more confident that the second TBM will pass with the same minor impact. Through the TBM cut intervention and the SCL cross passage, we are able to see and to record, and we keep records of all the excavations and to understand the geology and the behavior and the conditions of the Mercia Mudstone. And during the tunnel now, we do back analysis with the monitoring data, and we are using the TBM to optimize the tunneling parameters in order to maintain a better mining operation, mining performance in terms of reducing even more the ground. And at the end of the day, we will have there is a limited tunneling experience in Midlands, but through this project, through all this data that we are collecting, it will be a legacy, and we'll keep it, and we'll publish. We'll try to publish whatever we can, and through the HS2, of course, and for future reference, and for the upcoming construction projects, which will try to be built in here in Midlands. So thank you very much. Any questions, please?